নমস্কাৰ।
Hello. Hi, Dinant.
Hello, can you hear me?
I can hear you very well.
Very good.
You have to share your screen. I think that's just trying is working or not.
Yep, I will do my best. Yep,
morning.
I'll check.
Sharing is where it is another three dots, I think. Where is setting? Oh, no, that arrow down.
Do you now see my screen?
I cannot see your screen yet, but I can see. I can see. So there's a arrow pointing upside.
Hello.
Hello, good morning, good afternoon.
Yes, we can see your screen. Maybe you can make it full. Yeah, yes, okay.
Hello, good afternoon. Hello.
Is it audible?
Okay.
We can hear you, but can you mute all the microphones? Otherwise, problem. Some sounds like all other microphones will be muted.
You first want me to present myself a bit, then I can show myself.
Maybe they have some.
Good afternoon, everyone. So, am I audible?
Yes.
Okay, so good afternoon, everyone. My name is Sambalika, and I'll be the moderator for today's webinar. First of all, I would like to welcome all of you on behalf of the organizing committee of this webinar in this international webinar on flood hazard and risk assessment. And today we have with us two experts who will ITP College, Dr. Ritu sir, for a welcome address. Over to you, sir.
Hello. I am Dr. Mridul Kumar Hazarika, Principal ADP College. We are organizing this workshop. Welcome to all. At the very beginning, I extend warm welcome to you all to this international webinar. To you all to this international webinar on flood hazard and risk assessment. As we natural disaster and calamities cause severe trouble and hardships for human beings, There are various types disasters that affect human lives, such cyclones, flood, erosion, earthquake, and so on. The Northeast India is prone to flood, erosion, and earthquake. I am hopeful that through the thoughtful deliberations in this webinar, the resource persons will assess the disasters, especially flood that is creating havoc at present across the country as well as Northeast. I wish that participants will be highly benefited from the webinar, and I wish it a great success for this webinar. Thank you.
Thank you so much, sir. Now we will going to start our technical session. Am I audible? Am I audible?
Yes, yes, yes.
Okay,
Yeah.
okay. So before we start, before I request our first expert to share his experience, I would like to give a brief introduction about him. Our first speaker for today's webinar is Dr. Dinan Alkema from Netherlands. Dr. Alkema has a PhD degree in physical geography from Utrecht University on the application of 2D flood propagation models for flood hazard and risk assessment. Currently, he is working as the faculty of Geoinformation Science and Earth Observation, also known as ITC, at the University of Twente, Netherlands. And Dr. Dinan Alkema has been working in flood-related topics for many years, and his research interest primarily lies in flood risk assessment in developing countries of Southeast Asian region. Now I would like to request Dr. Dinan Alkema to deliver his talk. But before that, I would also like to request all the participants to mute all their mics to avoid any kind of background noises. Over to you, sir.
Okay, thank you very much. It's a pleasure to be in this webinar with you, and I'm very happy to share some of my ideas on flood risk and to give you a perspective on flood risk situation in the Netherlands. Although I do believe that there is overlap with many parts in the world, like for instance in India, Bangladesh, but also in Thailand, for instance. I see my good friend, Dr. Manzul Hazarika is also one of the speakers. And I've been working with him already for a very long time. Well, I do not really have anything to add to the kind introduction that I just received. So, so I will start with the presentation. Yep. And I now hope you can see my screen. Where is my
Yes,
presentation mode? Yep. Sorry, I left my mouse at home and now it's
okay.
creating some problems for me. Okay, so sorry for this technical hiccup. If there are any questions, I do not see any raised hands now that I have my screen on full. So I assume that the moderator will be so kind to collect the questions or to guide me if there are questions. But what I want to share with you is that disasters are not entirely natural. There is often, well, always, I would like to say, a man-made component in them. And I would use the flood as an example. of how this interaction takes place. And that is already the bad news, why we will see more of them in the future. Was there a question? No?
No, maybe.
Okay. So I start with a picture because I've been working in Thailand for a long time. My experiences in India are a bit longer ago. I've been working in the Dehradun region and in Orissa province. But lately more with Dr. Hazarika in Thailand and in Vietnam and other places in Southeast Asia. But I think these pictures are kind of familiar to you. You must have seen them, settlements underwater, shopping streets, even train tracks, causing society basically come to a stop, which causes economic damage, human suffering, and even deaths all over the world. And in the case of Thailand, and this is an example, even airports can be affected by these events. So what you need for a disaster are basically two components. One is the flood event. It can also be an earthquake, but my presentation today is about flooding. So you need to have a flood event, which is basically that there is too much water that the drainage system cannot handle. And on the other hand, you need something that can be damaged, something that has value. And the moment that these two overlap, as you can see in this graphic, then we call it a problem. So here you see a happy picture of two kids swimming in the street, but you can also imagine that this is causing economic damage and might even be dangerous, or health issues could come into play. So a disaster is when a flood event, in this case, interferes with society. And on the one hand side, you can say some things about the flood event itself. It has certain dynamics, it has certain how it develops over time and in space. It is triggered by something. Often it can be rainfall events, or it can be a dike breach. It can be a typhoon event. So there are characteristics like frequency and so on. So there is a lot of things you can do about flood, and flood hazard specialists are working on that. You can also model it using simulation tools. But on the other hand, you have society, and also society has their characteristics. A term that you may have heard about is vulnerability. So what is the ability of society to suffer damage, disturbance from a flood event? Some societies are very vulnerable and others may be less vulnerable. So these are characteristics that we can study and that we can maybe learn from. So what is there? Are there houses? Are there shops, companies, industry maybe, special facilities like a fire brigade or a hospital? And are people aware of the flood? Are they prepared? Are they experienced? Do they know what to do? And then if the flood is sufficiently severe and if society is sufficiently vulnerable, then you talk about a disaster. So it's the overlap of the event and society. In terms of terminology, what I say is, on the one hand, you have disaster, and on the other hand, you have disaster risk. And for me, disasters, we talk about disasters when there are real historic events. So they have happened in the past. We can learn from them. But when we look at the future, then we talk about risk. So then we look at the hazard of the flood. So what is the probability that a flood will occur? And then we look at society in terms of exposure. So what is there and what is the vulnerability of that society? So disaster risk is something in the future. So we try to, we study it, we simulate it, because we want to learn and we want to be prepared. And of course, we want to know how can we mitigate the risk? How can we reduce the risk? And what options do we have? Can we build dikes? Can we do more clever planning? These kind of things. Just a few statistics, just to give you an idea. So this is the, on the red line, it shows the number of people globally killed by disasters. And there you see that we are doing a very good job because the line is steadily decreasing. So less and less people are being killed. But if you look at the people affected or the number of disasters reported, that one is growing. So it says something that on the one hand, we are good at protecting human lives, and at the same time, the number of events is increasing. That has to do, of course, with better warning systems and evacuation of people, so that we provide shelters and safe places and give people the time to go there. However, damage is increasing and people affected is increasing. Here you see, for instance, a graph where we separate hydrometeorological disasters with earthquakes. And there you see that earthquakes are steadily increasing on the left-hand side, but that the hydrometeorological disasters are increasing exponentially. And this is, of course, a good evidence that climate change is affecting us more than we would expect if it was not there. So if you look at earthquakes, which is not related to climate change, you see a steady increase, which can be related to population growth or our societies becoming more vulnerable. But if you look at hydrometeorological disasters, they are growing much faster. So that is an indication that the events themselves are becoming more disastrous. Now going back to the risk graph, so that risk or the probability of future disasters is a combination of hazard on the one side and a vulnerable society on the other side. If the risk is growing, that can be because the hazard is growing on the one side, or that society is becoming more vulnerable. Now, the hazard can increase because of temperature rise, sea level rise, higher frequency of hydrometeorological disasters. I will see some interference. If somebody has a microphone on. Are there questions, or if there somebody wants to say something?
Maybe not.
Maybe not. I do not see you, so please let me know if something is if you have something to ask me, then I can of course pause and address your questions. But if not, I'll just continue. So the hazard can grow, but also the vulnerable society can grow, and that can be because of population growth, urbanization, so the concentration of more people in a smaller and exposed piece of land, bad planning, so that people are living in the wrong places. If you live on a floodplain, basically it's the wrong place to live. Unfortunately, a lot of people are living in floodplains. We should also not forget that our societies become more and more complex. We depend more and more on electricity. We become more and more dependent on the transport of goods for industry, but also for supermarkets and so on. So food security can be an issue. So society is also changing a lot, and we become more and more vulnerable. So even if the hazard would remain the same, there would still be an increase in risk because we make ourselves more and more vulnerable to hazards. Then, of course, the challenge is to do risk reduction. So what can we do to reduce risk in the future? The obvious answer is then to make our society less vulnerable. Of course, the million-dollar question is, what can we do? What can we do about it? Of course, we can reduce bad planning and that we do better planning. But that, of course, is not that easy. There is a lot of dynamics when you look at urban growth, for instance. You do not always control it. Look at the development of new areas, people coming into the city, which is unplanned growth. Or we can reduce the hazard, but who can control the climate? Who can control the rain? We can build dikes. That's one way to stop the flood from entering areas where it should not go into. And I'll come to that later, because that's, of course, a strategy that we have been doing a lot in the Netherlands and everywhere in the world, actually, building dikes, trying to control the rivers so that we live in a safe place. But even there are issues. So how to do risk reduction? Just to show you a few places in the world where huge floods are happening. And I usually ask the question here, where is the risk the highest? The top left is the delta of the Lena River in northern Siberia. Then the top right is the Mekong River Delta in Vietnam. And then the lower left is the Chao Phraya Delta in Thailand. So if there is a flood, and all these rivers do tend to flood regularly, where is the risk the highest? I cannot see you, but I do hope that after my presentation you understand that in an urbanized area like the Chao Phraya Delta, the risk is the highest because that's where the highest concentration of valuable property and people are located. But I can assure you that the floods in the Lena River Delta in Siberia are much higher. So there is a huge hazard, but there is very little exposure and very little vulnerability. Only some reindeer and nomadic people live there. And they're quite used to the summer floods of the Lena River. So that's why you never hear about the flooding of the Lena River in Siberia. And when there is a flood in Thailand, it is becoming world news. I also promise you to look a bit closer at the Netherlands. And I'm a geomorphologist by training, so I think I need to explain to you something on the morphology of deltas. Also, India has huge river deltas, and of course, close to you, you have Bangladesh, which is one big river delta as well. And there is a peculiarity about river deltas. They are at the end of huge river systems, and they are very convenient places to live. First of all, you have access to the rivers, which is good for transport, for drinking water, and so on. And it's also very fertile soil, so you can grow your crops. The problem is, of course, that they flood regularly. Now, what I have shown on this slide is cross-section through a typical part of the delta in the Netherlands, and the area that you see is the Rotterdam area. So I do not know if you can see my mouse, but this greenish area is the city of Rotterdam, and this is the Rotterdam harbor. And so we look a bit upstream from it, and if we make a cross-section through the surface of the soil, you see that it's alternating sandy bodies and clay areas intermitted with peat. Basically, traditionally, these were swamps. So the river are sandy because the sand is transported by the flow of water, and the clay and peat are there when there are flooding. So the clay is only deposited during flood events. Now, people used to live on the sandy parts because they were higher and drier, and the clay and the peat were swamps. But then people start to build the dikes, and then they encroached into the back swamp. There,
There's a noise. Somebody,
there is the noise.
yeah, Mr. Abu Sharma Ahmed, can you close your microphone? Abu Sharma Ahmed, yes. Okay, thank you. Go ahead.
Okay,
Somebody
maybe
else.
for those who have studied geology.
You can go ahead. I think it's okay now. Dinan, you're mute. Dinan, you're mute.
Yes.
Yeah.
I think I'm back. Oops.
Yeah. Go ahead.
Okay, good. So basically, this is some geology of the surface area of the Netherlands, but you will have the similar in Bangladesh and in all other big river systems like the Chao Phraya or basically any other delta that you can imagine. And it's important to understand because sand is a good material to build on. It does not compact that much, so it's stable ground. The problem with clay and peat is that it's swampy material. It has a high volume of water, and for people to live there or to do agriculture, it has to be drained. Now, people start to live on the higher areas. They build the dikes to protect them from the floods. But it also basically means that the back swamp areas are drier and drier and drier. And as they dry, they compact. So you have subsidence there. And the subsidence is increased because we started to build pumps to take out all the residual water. So there was artificial increase of the drainage. And there you see the arrows showing down that the polders are compacting and that there is subsidence. And I will make another slide here. This is, of course, the typical picture that we like to show to the world about the Netherlands, beautiful blue sky and windmills. I'm pretty sure that most of you, when you think about the Netherlands, you think of windmills and tulips. Well, it's true, we have a lot of windmills and they are water pumps. That's why we were constructing them. Water pumps, and not for grinding grain as they are used elsewhere in the world, but to pump out the water from the lower areas into the higher areas and into the river all the way to the sea. And this is basically how it works. So we have a river and we have a polder, and in the polder nowadays we use diesel engines, not the windmills anymore. So we have river in the water that drains to the sea. We have the polders, which are low-lying areas. There is rain coming into the polder and it's pumped out and then it's into the river system. And then what is happening nowadays? So is this sustainable, this way of living? And like I said, this is for the Netherlands, but in many other parts of the world, it's the same. A polder needs artificial drainage. Sea level change. That means that the rivers have a harder time to discharge into the river. So also the water levels in the river is increasing because of that. Now, because of climate change, it is also foreseen that there will be more river discharge. There will be more rain, more typhoons, more glacial melt, all these kind of things. So the river levels are increasing as well. And that means that we have to pump harder to get the water out of the polder, simply because the river level is higher than before. Another thing is, because we are pumping the water out of those peaty and clayey soils, they compact, and this is irreversible. So this is subsidence that is happening all over the world, and I think most of you may be familiar with subsidence in cities like Jakarta, Beijing, Manila, all these big cities that are in coastal areas on peaty and clayey soils, where they pump the water out because the citizens want to have, dry feet. They don't want to live in swampy areas. So the pumps are necessary to keep the area dry. But that also means that you're basically pumping yourself down. This is an irreversible process and is causing a lot of problems in many of the mega cities all over the world and also in the Netherlands. So we're pumping ourselves down. Polders are therefore low-lying areas, and they will be lower and lower and lower. And as you can see, the gradient, so the difference in height between the rivers and the polder area, is increasing. And that means that you have to put more and more effort into keeping the polders dry. Now then, if you expect climate change, also the rain discharge of the rain will increase. You have higher peak rain intensities. That means that it can be very difficult at times to keep the polders dry. And the people that live there, because these are the areas that we develop. I've just shown you the city of Rotterdam on the first slide. Yeah, the city is expanding because more and more people live there. I already mentioned cities like Jakarta, Bangkok, Beijing, Manila, Dhaka. People are moving into those areas more and more.
Some problem. Can you mute? No.
Am I now muted again?
No, you are okay. Go ahead.
I'm okay. 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 So that also another problem is that because the difference in height between the water level in the river and the soil surface in the polder is increasing, it also means that the risk of dike breaches is increasing, simply because the pressure on the dike is getting higher and higher. And here you can see what happens when the dike is breaching. Then water flows into the polder and is starting to fill up the polder. And of course, you have the deepest water levels at the lower end of the polder. But polders are usually crisscrossed by river dikes. And so if there is a dike breach, it will be compartment by compartment. But eventually, the whole polder will simply fill up like a bathtub, basically. So that's why it's very risky to live in a polder, because it's like living in a bathtub, basically. And if then the dikes break, you have a severe problem. And of course, that is then a bit of a dilemma, because you build the dikes to prevent the flood. People feel safe because they live behind the dikes. But if the dike fails, then the problem becomes worse, because then people are basically living in bathtubs and then try to evacuate people in time. That is a very challenging job. And it's one of the things that people, when they live in these areas, they feel protected, that they do not realize that. So this is another example. So if the dike breaches, what is the risk in the areas of the people living there? And then what is the situation, for instance, if it's like this? So it's quite difficult also for planners, people living in that area, to predict how bad the flood will be. I think that was my presentation. Maybe there are some questions or comments, or maybe you want me to explain a bit more. Hmm.
Vinod,
Yeah, I'm trying to stop.
yeah, maybe any questions and comments we can. Yes.
Any questions? Was I so clear that you understand everything? Then I will want you as my students.
No, there is no
Please.
question in the chat box.
Thank you so much, sir. It is really an honor and privilege to have you in this webinar. Thank you for taking your valuable time out and to join us in this webinar and for sharing your valuable knowledge and experiences from Netherlands with us. And thank you again. And if the participants has any question or queries, please ask your questions to our expert. Or you can leave your questions in the chat box as well. Any question from the participant? Okay,
Somebody raised a hand.
Okay.
Abu Shama.
Yeah, he should ask the question.
Abu Shama Ahmed, can you ask a question?
Abu Shama, do you have any question?
Yes, he's mute.
You have to unmute yourself.
Yeah, no.
Okay, so
maybe later. Maybe
Yeah.
later.
Yeah, maybe okay. So if the participants has any question, you please give your question in the chat box. For now, we will move to our next session. So, thank you, sir.
Yeah.
I would also like
Okay.
to
I will.
our expert, Dr. Dinant Alkema, sir.
I will remain available. So if there are questions later on, then you please
Yes.
please ask them.
Okay, sir. Okay, yes. Thank you, sir. Now we have our second speaker for today's webinar. Before I request our second speaker to deliver his talk, I would like to give a brief introduction about him. Our second expert for today's session is Dr. Manjul Kumar Hazarika. Dr. Manjul Kumar Hazarika is currently working as the Director of Geoinformatics Center in the Asian Institute of Technology, Thailand. Dr. Hazarika holds a PhD degree in Civil Engineering from University of Tokyo, Japan. He also holds an Masters of Engineering degree in Remote Sensing and GIS from Asian Institute of Technology, Thailand, and MTech degree in Soil and Water Conservation Engineering from IIT Kharagpur, India. Over the past 20 years, Dr. Hazarika has been working extensively on applications of geospatial technologies in agriculture, disaster management, and the environment. Over to you, sir.
Thank you very much. I think some of the microphones need to be muted.
To avoid any kind of background noise, I request all the participants to kindly mute their mic.
Sure, yeah, okay. Okay, can you see my screen?
Yes, sir. Yes, sir.
Okay, thank you. So, good afternoon. It's my pleasure to talk about flood hazard and risk assessment concepts and practices. I think Dinant has already given an overview but I'll be going a little bit more details so that the concepts are getting more clear, because I know many of you are new to this kind of subject. So I'll try my best to tell you what are the concept behind all this hazard and risk assessment, and also some of the practical applications we have done. And we have done a lot of work with Dinan and his colleagues from ITC in many countries. Okay, so first defining the risk. So for example, you have this say stone, this is a hazard. So, and this hazard, if the stone comes, then it will, sorry. So if the stone comes, then this two buildings will be damaged. But the damage for this left side building, which is your RCC building, it will be less damage. If the it will
মানে আসলে আমার হেরেই না যায়
Mr. Ansari Latif, you have been Mr. Ansari, can you Mr. Ansari, can you mute your mic?
বন্ধ করি মানে কুইট করে দিন হ্যাঁ কুইট লিভ করে দিন
Okay. He many times he is doing the same. Okay. So then these left side buildings are less vulnerable, because even if this stone come, it will be less damaged. But this right side house will be completely damaged, so it's high vulnerable. So now, if this building, left side building, is high exposure because it's near to the source of the hazard, okay, and right side is low exposure because it is away from the source. So if house near the river will be highly exposed to flood, but the house away from the river will be low exposed to the flood. So you can calculate the risk hazard into vulnerability and the amount of this damage of these buildings. So this is also Dinan already explained. So if you have a hazard and a vulnerable society like buildings or whatever, then there is a risk. And the moment this hazard happens, the stone comes down, then it will be disaster. Then how much risk you are carrying, again, it depends on your exposure and vulnerability. All these things matters. So with this, also the risk is a geospatial problem. And for example, there is a river, and they are along the river, these are the buildings, industry, whatever. So when you say hazard, flood hazard, how big is the flood? Is it a 10-year flood, 50-year flood, or 100-year flood, or 200-year flood, or 500-year flood? So this number, 10, if you are expecting 10-year flood, it is it's called a return period, it's a small flood. 50-year will be bigger, 100-year will be big flood. So this return period increases, means your severity or intensity of the hazard will be very high. For example, if you look at the 2004 tsunami in the Southeast and South Asia, you can there are hundred thousands of people who have died, but the return period was almost, I think, 400 years. So more return period, you can expect much bigger hazard. So then exposure is if a flood happens, you can see in the figure how many buildings, what are the buildings are inundated. That is your exposure. And vulnerability will be how much damage or loss caused by the flood for these buildings and infrastructure. So 3 things: hazard, exposure, and vulnerability. So this should be, if you have any questions, I'll explain later. You can ask me a question. Okay, so now this hazard and exposure part, which I have mentioned here, is you need, it depends on environmental factor, triggering factor, and hazard inventory. For like geology, soil, land use, all these things are topography, hydrology. Triggering factor, for example, flood will be triggered by rainfall. Heavy rainfall happens for a few days, flood will be triggered. And also hazard inventories like flood last, say 30 years or 40 or 100 years, how many floods happen. So those kind of, and what intensity, all this information is required to assess the hazard and exposure. So this is one part. The second part is vulnerability. Vulnerability of the buildings and infrastructure. So if a building is a single-story building, it will be highly vulnerable to flood. If a double-story or triple-story building, it will be less vulnerable because people can go up, they can take their belongings to up, so it will be less vulnerable. And this, again, the quantity, amount and number, how many buildings are exposed to a flood, and that created the risk. So this amount or number is also important. So here there is a security factor, livelihood, literacy, gender, poverty, culture. Normally we ignore this part because it is very difficult to quantify. So in many cases, normal we call quantitative flood as a risk assessment. In that case, we ignore the socioeconomic factor, but we can do it. That is called qualitative flood risk assessment. But in this case, I'll talk about only quantitative. So a hazard, you see the 5-year flood, 10-year, 25 or 100-year flood. So this is, you need to do model or some observation or some field data collection. You can prepare this hazard map. Then right side, this element at risk, building, infrastructure, all those things. And you put together the hazard map and element risk, and you can find the exposure map. Means these are the building and infrastructure exposed to the flood. And for each building and infrastructure, you can do some data collection in the ground. This horizontal x-axis is your flood depth or flood intensity, and vertical one is your damage. So if you look at, these are 3 types of building. The top one, the red one, is a these are the buildings which are like a very single story, very average quality house, which like Assam type house. So as flood increases, your damage increases very rapidly. But if you look at the bottom one, it may be RCC building and 2-3 stories. So even flood increases, your damage remains same because people go up, they take their belongings to up. So in that case, it is less vulnerable. So then you multiply all these things, then you get the risk. So, but one big difference you should know is that there is a big difference between hazard and risk. So, as Dinan also mentioned, that a flood is happening in Siberia, nobody is there, not many people are there. So, there is a flood hazard, but there is no risk. But here, although see, this is the same area, flood happened, lot of flood happened here, but there is not many infrastructure buildings, so you don't have much risk. But in some area, left side you see, in this area, there are a lot of high risk because you have high value infrastructure or buildings or factories. So if a small flood comes, you can expect large damage. So the flood map and risk map is 2 completely different things. It should be to have the risk map, you have to have the all this infrastructure, as well as some sort of flood, some flood should be there. Then it will be, you can produce this map. So normally, traditionally, we look at the flood map. So if you look at the flood map, you will be doing protection in this area. But I think it is not advisable because you don't expect too much losses from this area because there is no infrastructure. But here you see, although it is away from the flood area, but still some local flood is happening and there is a risk. So be mindful about this. Then hazard assessment, what is, as I said, we need to know the probability of occurrence of the hazard, that is flood, for a certain severity, for a specific period of time for a given area. For example, if you say, Mr. Abu Samar, can you mute your mic? You have been always. Yes, thank you. Okay, so this is, for example, you want to have some flood hazard map in a particular location, say Morigaon. So you need to have this flood map, past flood data on those areas. Then you can prepare this kind of hazard map. Basically, flood hazard, you can have flooded area, volume of water, and the site, it will give it a flood depth. So if you have a, say, 10-year flood, it will be less area flooded, less volume of water, and less depth of water. But if you go for a 100-year flood, it will be large area flooded with lot of water and very high depth of water. So this kind of thing. These are some others. I'm just focusing on flood here. Then you can do the risk, this hazard assessment using, say, flood river research and the extent or depth of flood. So it is called frequency magnitude. So for that you have to have flood data of that location, and you do this modeling, and you can get a flood map like this. So So for example, this is again, this I have taken from ITC or earlier some of the training programs. They have simulated this one in one of the city in South America. So this is hazard map. So this is your 10-year flood hazard. This is your river. This is your 10-year flood. This is your 50-year flood, bigger than 10-year. Then it is 100-year flood. So if you go for, this is during winter, no flood, then flood is started, then this is big flood, this is very big flood. So this kind of, then this flood, how many buildings and infrastructure inundated, those are the exposed. Then you need to estimate, calculate the how much damage expected from some field survey. Then you can prepare the vulnerability, that is damage from this flood for this all buildings exposed to this particular flood. So you can see this one, 10-year flood, red one, then the brown one is 50-year flood, the yellowish one is 100-year. This is a big one. It can also 200-year flood, 500, you can do it, depending if you have data. So information required for hazard assessment is understanding the factors influencing hazard occurrence, long-term observation, as I said, for historic reports on past incidents of hazards, frequency and severity of the events, scientific industries, studies, maps, etc. So next is vulnerability assessment. So vulnerability is defined as degree of loss for a given element at risk, that is the building or any other road or whatever, resulting from a hazard at a given level of intensity. Intensity means if a 1 meter flood, this much damage. 2 meter flood, more damage. 3 meter flood, more damage. So those 1 meter, 2 meter, these are intensity. And then for a full definition of vulnerability, it is expected damage level at every level of severity of the hazard need to be defined. As I said, 1 meter, 2 meter, 3 meter, 5 meter, something like that. And most of the disaster mitigation work or risk reduction work, it is focused on reducing the vulnerability of the buildings and infrastructures. So vulnerability assessment, it is important to develop planner to make some effort to quantify tangible aspects of vulnerability as well as to and loss to assist the mitigation preparedness planning. So this is a physical side of the vulnerability. The other one is socioeconomic, those are intangible socioeconomic. Those are we call qualitative vulnerability, and these are the quantitative. So building, infrastructure, crop, livestock, we can identify the damage or loss from some field survey. So again, same thing. This is physical one. There could be different kind of vulnerability: physical, economic, environmental, individual, social, all those kind of things. But we will be focusing on physical vulnerability, like type of buildings, and then what is the detailed survey you have to do, type of building, quality of building, all those things. So this is the same thing as I mentioned already. This is your flood depth. This is a damage for different kind of buildings. So if we have say in Nagaon, you have 10 types of buildings, and you have to develop this curve for all the 10 types of building. So now, this is, you can see, these are the land parcels. So it was ITC did work here. This is the same river, and this is a 100-year flood. And this land parcel, these are the here red, the dark black one is high degree of vulnerability, brown one is high, red one is moderate, and yellow one is low degree of vulnerability. These are the land parcels. It could be like, for example, residential area, commercial area, then it could be industrial area, something like that. So this black one is, you see, one single story building. So that's why if flood comes, you can expect high damage. So vulnerability is very high. This yellowish one is 3 floor or more, these buildings in this area. So you can expect less damage. So they're less vulnerable. So for vulnerability assessment, you need hazard characteristics of the element that is building, infrastructure. You need to know location and site, structural strength or quality of this element at least, or these buildings you need to know. So this is one example I am giving you. So there are 4 houses, and this left side is above the flood area, so it is a risk-free. These houses are, this is 10-year flood, means probability 1 in 10, so you can see the hazard 0.1 in all the cases. This house say 50% inundated, so we say this 50% damage we expected is just theoretical exercise, so it's a 0.5. The right side is very little inundation, so we expect 20% is 0.2, and this one is up to the ceiling water, so it is 100% vulnerability, so 101. So and this cost of the building and the contents inside is 100,000. So these 3 buildings, left side one, you can expect a damage of $5,000. Middle one, $10,000. Right side one, $2,000. So total damage you are expecting $17,000. Now you put them, then how much you save? That's an important question for decision making. If this dam costs say $100,000, but you are saving $17,000, so there is no point of doing this. In that case, maybe you can do something individual level. You can do this kind of risk mitigation method. So this risk assessment will help you for decision making. But normally, this kind of dam, if it is a rural area, you may not. It may save some agricultural area, some houses, but the cost-benefit ratio will be less. But if this is a urban area, town area, city area, then cost-benefit ratio will be very high because a lot of buildings will be submerged and you can expect high damage there. So Then again, land use planning. So the government may decide, okay, this is a high risk area, red one, nobody lives here. So then they move the people outside. Maybe then the medium risk, you can have restricted settlement, not too many. But this kind of thing in democratic country, very difficult. But in some of the countries like China and all, they can do this because they can remove the people at their will. That's not a problem there. Okay. So now this is only given, I have given one scenario, but there could be 2-year flood, 10-year flood, 50-year flood, even 100-year flood. So you have different scenarios. So with climate change, this intensity or depth of flood will be increasing. So in that case, you have not only one scenario, several scenarios. If you make the flood risk for more than one scenario or many scenarios, then it is called probabilistic risk assessment. This is called deterministic. One level is deterministic, and this is called probabilistic. So normally in most of the countries, they use the deterministic flood for 100 years flood. Normally this is the standard. But given the climate change and other things, I think now it is important to probabilistic risk to see the different scenario. Then you decide which level you want to make mitigation measure for, because the mitigation measure for 2 years will be less. If you go for 10 years or 50 years or 100 years, mitigation measures will be high because you have to make high levees or dam height is more, right? So that kind of thing. So again, we have flood hazard map, you have vulnerability map, and you have this damage in each land parcel or buildings. You have some field data, and finally you make this risk map. So you can see these red points here. The black one is the highest risk, 2 million to 3.96 million. You can expect damages. So these are high value land parcels, maybe industry, maybe some commercial areas. Then you have to probably protect these areas first. If you make some mitigation measure, you can save more losses and damages in this area. So it will give you some urban planning or city planning, better city planning or urban planning you can do. So application of risk assessment, risk sensitive development planning, just I explained. Provide good basis for advocacy and create awareness among policy or decision makers. Helps to get political support and mobilize resources. If it is high risk, you can mobilize support. Helps in cost-based analysis for prioritizing DRI investments. So as I mentioned earlier, so whether you want to dam or raise your buildings or some land use, so for everything you can have some kind of cost and benefit. If I do this, how much cost and what is benefit? So this kind of applications are there. Risk assessment are now being commissioned in many cities around the world, including India. So we have done one risk assessment in Uttarakhand. It is around whole state, Uttarakhand. And we did it sub-district level risk assessment in the Uttarakhand state. So you can see that these are the baseline data, population, built up areas. This is very important. Lifeline like telecommunication line or other power lines, those kind of, not that the lifeline means the important buildings like hospitals, power stations, then government offices, police station, those kind of things. These are the buildings. Then tourism area. As you know, 2013, Uttarakhand is a very big disaster, cloud burst. And after that, the World Bank initiated this risk assessment project, and we participated in this, and we did with 2 other firms together. This is agricultural area in Uttarakhand, and this is industry and commercial area in Uttarakhand. So all this data you should have. These are called element at risk. Then also we collected ground data for 15 types of buildings you can see in Uttarakhand. All these buildings, we collect data. If earthquake comes, which one will be highly vulnerable to earthquake or quickly damage or maximum damage, or if flood comes, which one will be affected, how much damage, all those kind of information we collected. Then 27,000 buildings from 500 locations were data collected in the whole Uttarakhand. You can see the distribution. And we can also prepare hazard maps. There is earthquake hazard map, flood hazard map, landslide hazard map. So flood is, the upside is Himalaya hill. So you can expect flood in the plains in the south, right? This area is the Haridwar area, this left side. And also landslides. So this multi-hazard risk for overall annual loss you can expect is very high actually from earthquake. 97% is for earthquake in Uttarakhand. Flood contains only 2.6%, and you can see the sector: residential building, economic sector, transportation, critical buildings. How much percentage if a big earthquake comes, or how much and flood comes, how much damage. Okay, somebody. Okay. So Abdul Ghani, yes. Okay. So we did also some flood risk in Haridwar area, which I have already mentioned. This many of you already know Haridwar as this part in the south part of Uttarakhand. So you can see the different flood law risks from Haridwar area. So different, you can see economic sector, residential building, transportation, critical facility, power infrastructure, all those things. Then also there are a lot of risk assessment platform. One was CAPRA. It was, I think, 15 years ago, World Bank started. So this is one city. So what are the high risk area? This red one is high risk area. This greenish one is low risk area. And then if a bank give you a loan, if you put your industry or investment in high risk area, then you have to probably insure, and we have our interest will be more because you are putting things in a high risk area. And also this government, local government planning. If you know the risk map, you can do the planning better. Which area is safe? What kind of installation or buildings or critical facilities you can put. So this is, and everybody is a part of this this process. As a citizen, you should also know where you are and how much risk you are taking. And depending on risk, if you insure it, then your premium will depend on where you are. High risk area, you have to pay high premium for insurance if you're insure a house and other things. So CAPRA, I think it is not anymore available in open source, but it is owned by a company. They still continue. But the World Bank tried to make it open source, but it failed actually. It can do earthquake, flood, hurricane, landslide, tsunami, and volcano, and it's a probabilistic risk assessment. So we, together with ITC, we have developed this one, risk changes. where you can have vulnerability graph exposure analysis, loss analysis, risk analysis, and risk visualization. This is very new. This is in open source. So you can go to this website, riskchanges.org. You can work on it directly. It's a web-based platform. If you want to do risk assessment, you can do freely in this one. So it's a multi-hazard, any kind of hazard, possibility of integrating climate change information. This is our plan. So it's multi-hazard, multi-asset, vulnerability database, multi-user compare risk, and spatial analysis. So this, we just completed this platform. We are now starting giving training in different countries, and also we are looking for implement some projects using this platform in future. And also, if you go inside, you can also, there is a demo inside. You can say debris flow or flood, how many years, current situation, what kind of alternate measure. Then you can see what is the risk in. And so this is a kind of, you can play with if you go into the riskchanges.org. Thank you. Any questions? Any comments?
Thank you so much, sir, for sharing your in-depth information and knowledge on flood hazard and risk assessment, its concepts and practices. Now, if the participants has any kind of question or queries, you can ask to our experts. You can leave your questions in the chat box as well. Okay, so I think we don't have any questions from the participants. Also, a little update for all our participants that we have shared a feedback link in the chat box as well as in the WhatsApp group that has been created. I request all the participants to kindly fill up that feedback form because after that only we will generate your e-certificates. And now, as we're heading towards the end of this webinar, I would like to request PM Raina sir, Program Coordinator of this webinar, to deliver a vote of thanks.
Good afternoon, everyone. We have reached the final and last session of our today's international webinar on flood hazard and risk assessment. So at the very outset, I would like to extend my heartiest thanks to the organizing team of this international webinar under the guidance of our Honorable Principal Sir, IQSA Coordinator, and our Honorable Resource Person, Dr. Dinan Alkema, who has dwelt on the topic flood hazard and risk assessment experiences from Netherlands. Through the deliberations of Dr. Dinan Alkema, I think that the participants has been highly enlightened and they have learned a lot. Then our another participant, I would like to extend my heartiest thankfulness to Dr. Manjul Kumar Hazarika sir. He has brilliantly spoken on flood hazard and risk assessment concepts and practices. So we, the organizing team of ADP College, would like to extend our heartiest thanks to both the resource persons. Now I would like to extend my vote of thanks to participants from Assam and the entire Northeast and the professors of different colleges and universities. Now, last but not the least, I would like to extend my heartiest thankfulness to the technical staff, particularly Dheeraj Kumar Bora, Afifa Kausar, and Ambalika Fanglo from our college. So with this note, today we are going to close the session. Flood hazard and risk assessment is over. Thank you. Thank you everyone for your kind participation.
Thank you. Bye-bye. Thank you, Dinant. Bye-bye.
Thank you all for listening, and it was my pleasure. I wish you all a very nice evening.
Thank you.
Manju sir, you speak yours.
Bye-bye.
So this webinar has ended now, and yes, the webinar is now ended, and the participants can leave the session now. Thank you.